Uh, Good afternoon, everyone. My name is Hanna Kontinen, and I will be acting as the custos in this public examination. Today, Matti Heino will defend the doctoral dissertation titled Complex Systems and Behavior Change, Bridging Faraway Lands in Social Psychology at the Faculty of Social Sciences of the University of Helsinki. It is a great honor to have Professor of Psychological Sciences Kerry Maas from University of Connecticut as the opponent. As the custos appointed by the Faculty of Social Sciences, I declare this public examination open.
So we are here to conduct a public examination of the dissertation thesis of the candidate. And to start off, I will be presenting a few remarks about the context to provide the context for the scientific significance of the thesis. So we may ask, why has this problem, the aims and approach of this dissertation, been deemed worthy of public examination? And also, to what areas of science is it aiming to contribute? Now, we might think from one perspective that the importance of the topic of this thesis lies in the domain of behavioral science, and in which we're focusing on tackling behavioral change processes and dynamics of related phenomena. And fundamentally, being able to influence human actions is quite important scientifically, also an implied way, so in that in order to impact various kinds of problems affecting the spread of disease in humans, improving human health and daily functioning, being able to understand how to change behavior is key. But if we focus fairly narrowly on that perspective, I would argue that would substantially understate the situatedness of this thesis in terms of its scientific significance of this particular focus. Rather, I would suggest that the goals, the aims of this thesis in science, I would argue is much less conventional, much more radical and more lofty a scientific goal. So the thesis isn't, for instance, focused on a specific area of motivation or behavioral change, testing in a series of interrelated studies, a specific set of hypotheses, in one particular domain. Rather, its goal is to attempt to make inroads on really the very fundamental scientific basis of conducting such research. Now, the behavioral change field does have, many strengths. I mean, it draws from quite a great breadth of processes, from perhaps the oldest concept in social psychology of attitudes to newest understandings of a whole host of different processes, normative processes, in-depth focus on motivation, social cognition, and planning processes. But like many of the individual research areas that behavioral change science draws from, the meta-theoretical assumptions that underlie its approach to the science in its essence is in many ways quite traditional, conventional science. Now, those methods and questions are really quite useful, very powerful tools, but they're constrained to a rather narrow range of phenomena, the linear realm, and the realm of understanding causality in a mechanistic way. In contrast, if we think of the most kind of cutting edge approaches to science, thinking about, for instance, within the biological systems, sciences who study physical environment, the natural world, ecological scientists who study climate change, for instance, they understand that the various influences on some biological or natural outcome isn't accurately really understood through a paradigm of mechanical systems in which you try to understand an object by taking apart the object into separable components. Rather, they understand that processes are really fundamentally can be nonlinear, involve coupled and interdependent systems, in which the kind of connectedness, the kind of interdependency of these components yields rather novel emergent properties that couldn't be predicted from merely a sum of the particular parts. So this thesis is picking up that those kinds of meta theoretical perspective, that kind of paradigm, to advocate for this cross-domain innovation in a viewpoint that focuses on nonlinear processes, interdependency, interconnectedness. In part, this means new statistical tools, analytic and visualization methods, of course, but more critically, I would situate this thesis in the goals of trying to move the field of social psychology and related studies that study behavioral change towards drastically updating the very paradigm for considering these processes, and updating that to a paradigm that's more appropriate for understanding the dynamics of behavior change. That is, and as well, other issues such as resilience, lack of resilience of such change. Now, the paradigm he's advocating is the perspective of complexity sciences. That one could argue is more appropriate for understanding the dynamics of behavior change. It also offers new tools. All of these things are excellent. But on the other hand, it is much more challenging than what are currently the conventional approaches in much of these areas of research. So that is a quite challenging goal, to take steps towards changing the very paradigms of research in behavioral and social psychological sciences. So with those challenges in mind, we should next hear from a summary of the research from the candidate. And afterwards, we'll examine the details of this.
Thank you, Professor Marsh. Thank you, dear Kustos. I will next first share just a single slide that you are seeing. And I need my notes. Honored Kustos, honored opponent, members of the audience. So the research I'm presenting here today explores the intersection of two scientific domains that might seem at first glance somewhat distant. And what I want to do here is share a little bit about why I think that building bridges between these complex systems and behavior change is not merely an academic curiosity, but a vital step into deepening our understanding of human action in this interconnected world, and ultimately towards building a more robust basic science of behavior change. And to begin with, I want to speak a little bit about the difference between making fruit salad and baking bread. And I'm very well aware of how ludicrous this sounds, but I do believe that confusing these two processes consistently causes well-meaning efforts at understanding behavior change to stumble. So please bear with me. Now, first, imagine making fruit salad to a bunch of children. So what you do is you gather these fruits you enjoy, maybe pineapple, peach, cherries, and you're fairly confident that if you like them separately, you like them together. So you chop them up and you combine them, and then you serve them. And if then a child finds that the cherries just look too weird to be edible and leave them behind, it's no disaster because they still could consume the pineapple and the peach, which every reasonable person does enjoy. And the uneaten cherries can be consumed by someone else later. So in fruit salad, we can combine these ingredients. We can analyze these parts somewhat independently and predict the outcome of the whole with reasonable certainty when we put the parts together. And with many, many ingredients, fruit salad can even become complicated. And this is a word whose origins can be taken to mean folded. So what has been folded can often unproblematically also unfold it. But now think of baking bread. So you combine yeast, flour, water, salt, and you've heard that olive oil is healthy, so you pour a bit of that in. So you mix it, you knead it, you let it rise, and you bake, and the final loaf emerges. But what if the children dislike the taste of olive? You cannot simply remove the oil. Or what if you put in too much salt? The ingredients have interacted, they have transformed. The bread is now an emergent product, which is something entirely new and fundamentally different from the mere sum of the ingredients. And the whole portion that was intended for the children and not just the offending component might have to be passed on to an omnivorous family member. And this process here is perhaps better described as not as complicated, but as complex. Complex is a word with roots that can be interpreted as being like entangled or interwoven. So unlike with this sort of a folding process, what is actually interwoven cannot easily necessarily be disentangled without fundamentally changing the nature of the system. So with this analogy in mind, let's turn to the disciplines central to my research. And the first one is behavior change science, which is an inherently interdisciplinary field, drawing from psychology, sociology, public health, and more. And it strives to understand the web of factors, personal, social, environmental, that shapes our actions. And its goal is to help foster these changes needed to tackle major societal challenges, for example. So from non-communicable diseases entailing, for example, physical activity behaviors, and sustainable work life entailing, for example, job crafting behaviors, to climate action and pandemic preparedness entailing different kinds of risk management behaviors. And human action, human behavior is a core thread running through all of these pressing issues we face. So this was behavior change science. So the other discipline, central work, is complex systems science. And this field originally grew out of physics, chemistry, and biology, but its principles increasingly reach out into the psychological and social world. It studies these systems composed of many, many interacting parts, where these interactions often dominate the system's overall behavior. And a key insight here is that it's the relationship between the components that can be more critical than the components themselves in determining the system's properties. So you can, for example, you can think of water. So we have ice, we have liquid water, and we have steam. And these all have exactly the same H2O molecules, but they're different patterns of interconnection. So how tightly they are connected to each other lead to vastly different properties. So steam can make a sauna feel warm, and ice can make swimming difficult afterwards. And it's the interactions that count, not necessarily the components, which are the same in the steam case and the ice case. So when it comes to systems, some are more component dominant like fruit salad, while others are more interaction dominant, like bread. And my research argues that many phenomena central to behavior change science, like motivation dynamics, the spread of social norms, or how people respond to interventions, are far more like bread than fruit salad. And they occur as parts of these complex interaction dominant systems. And some of the main contributions of my work relate to the development of a basic science. And so early theories in behavior change were driven by practitioners aiming to understand the issues they faced. And practitioners are often very good in working with complexity. Although their terminology to describe the phenomena at play might be sometimes limited. But still, so we had these early theories that were, to my opinion, quite reasonable, and they also discussed these complex factors and nuances quite in an interesting way. But the quantitative tools that were relied upon in developing these theories, then they implicitly treated behavior change phenomena like fruit salad. So for instance, interaction terms, to account for some forms of interdependence, its main usage has been to assign values to variables such as norms, intentions, attitudes, assuming that they are independent from each other, implying separability. So furthermore, there's also a common, often implicit assumption that findings derived from group-level data directly translate to understanding how individuals change over time. So the central question becomes, if behavior change is often entangled and emergent like bread dough, should our primary tools be those best suited for slicing this separable fruit? And I argue that this potential mismatch, analyzing bread with fruit salad tools, can hinder our understanding of behavior change as a complex, evolving process. And complex systems science suggests that this variability, which might look like messiness or error from a purely linear perspective, is often not just noise, but it's sort of the inherent signature of the dynamic system itself. And a key characteristic of these systems, which I investigated conceptually and empirically, is non-linearity. So you can imagine pushing a boulder near a hilltop. You push a little, the boulder moves a little. You push a little, the boulder moves a little. You push a little, and the boulder dramatically tumbles down into the valley below. And maybe at this point, some behavioral scientists rushed to the scene to investigate what was distinct in your technique for that very last push. And they will inevitably find results if they're careful. But the magic was not in the push, but in the relationship between the push, the boulder's position, and the landscape below. And this kind of an abrupt, disproportionate change is known as a critical transition in the literature. And complex systems science offers these powerful conceptual tools to map these transition dynamics, one of which is the attractor landscape. So what you can do is imagine a pool table with a single billiard ball. And each position of the table represents a possible state for the system. And the system's current status is represented by the location of the billiard ball. And now also imagine that the surface isn't flat, but it contains these hills and valleys. The valleys represent these stable patterns, sort of like what are called attractors, collections of similar states that trap the ball. So it's easy for a ball to settle into a valley, but it requires more effort or perturbation to push it out of one. And the ridges between these valleys are called tipping points. And for an example, you can imagine smoking, where dispositions in the North Atlantic world shifted gradually, if at all, for many, many decades preceding the 2000s. And you can imagine this as a ball residing in the attractor. And here on the other side of the original attractor is another attractor. And what happened was that during these many decades of gradual or ineffective seeming efforts, at some point the ball reached the tipping point, and when a system is at its tipping point, it can reach a new state or a new attractor very, very quickly. And so what happened was that we were first in the attractor where smoking was accepted or even encouraged by doctors. And then we moved to this place where there were many policy changes and that restricted people's ability to smoke, and smoking became something that was frowned upon. But now what's also important in this sort of landscape analogy is that these attractors are not necessarily stable. But what can happen is that the landscape itself shifts. So in an intervention, for example, what might happen is that the original attractor slowly grows less and less deep, more shallow, and until it reaches a point where it's very easy for the system to shift states to a new one. So you may notice how different this landscape representation is from conventional flow charts suggesting these neat linear causes and effects. And it shifts our focus towards understanding the system's dispositions, its underlying tendencies and stabilities. And it encourages a focus on nurturing the conditions, tending the substrate, working the soil from which these desired behaviors in deeper, more stable valleys can emerge and sustain themselves more naturally. So in my research, I used analytical techniques adapted from dynamical systems theory to investigate empirical evidence for such attractor states and shifts within this fine-grained individual level moment-to-moment and work mode data. And I also explored its applicability to societal level data on COVID-19 protective behaviors. And this work suggests that the landscape metaphor is not just a useful theoretical vehicle, but that these patterns can be observed and studied in real-world behavior change contexts. So in addition to this non-linearity, some of the other patterns of complex systems I examined in this research were, for example, non-stationarity and non-ergodicity. And in my work, I clarified these terms in the behavior change context and demonstrate how to study them empirically in time series data with methods such as cumulative recurrence network analysis. And I also investigate how behavior change researchers can make use of visual data analytics and psychological network analysis in the absence of longitudinal data. So in essence, the core message of this work is that the bread-like complexity of human behavior change is not just a noise or a problem to be necessarily simplified away. But it can be a fundamental characteristic we must embrace and understand scientifically if we want our science to accurately reflect the phenomena it studies. And complex system science provides these concepts and tools that acknowledge the interdependence, emergence, and context sensitivity of change phenomena. And what we aim to do with this complexity is not to eliminate it, but to enlist it. So by building bridges between science and complex system science, the research presented here argues that a complex systems perspective can help us build a more robust and realistic science of human action, one that recognizes behavior not just as a collection of separable ingredients like a fruit salad, but as an emergent interwoven process like baking bread. And this, I believe, is quite crucial. It's crucial for developing a science better equipped to understand the intricate dynamics of behavior change. It's crucial for us to seize the opportunities that arise when we learn to converse with complex systems instead of just trying to push them around. And it's crucial for navigating the critical policy challenges of our time, which invariably involve understanding and influencing human action. Honored opponent, I now invite you to present your critical comments on my dissertation.
Thank you. So we shall start with the title, Complex Systems and Behavior Change Science, Bridging Faraway Lands. This does capture quite well the content of the thesis, that there is a considerable gulf between the current state of behavioral science, behavioral change science, and the underlying assumptions and approach of complex systems. The subtitle, Bridging Faraway Lands, is a nice allusion as well to the attractor landscape sort of notions that underlie many of these ideas. So we'll start. I do have some bigger picture questions following from your overview. What I will start with first, though, is talking about specific questions or comments, some that are bigger picture, some that are fairly specific to the particular content of the paper. So don't hesitate if I'm not clear enough about what I'm asking in terms of the text, or what I'm saying is ambiguous in terms of the question. Don't hesitate to ask for clarification. So I'll start first with referring to what you referred to as Article 2 in the thesis, the 2021 paper, studying behavior change mechanisms under complexity, in which you're really presenting the case for really explaining how key kinds of features of dynamical systems, nonlinear dynamical systems, complex systems can be applied in behavior change mechanisms, and also use data to illustrate that. The data that is used in this is the work motivation data that you referred to. Well, I just start first with the issue of on page 4 of the 22, for instance, and this comes up several other places, that what you're arguing for is that contextuses should be specific to the individual. And in fact, the very assumption of non-ergodicity is that individual processes, as you argue on the next page, I believe it is, should work on the individual. So I think one question I might have is that, first of all, people may often consider that what we are trying to do is build a science of generalizable knowledge. Does this put into question the very nature of being able to build a science that conveys a generalized knowledge? It might well be useful for someone in an intervention to know where a particular individual is with regard to their the state that they're in. But yes, is this challenging then for being able to build a science that will give us a generalizable knowledge?
Yes, I think that what is currently done is that we are missing one step in building this generalizable science. So what we do is we take these groups of people and we often average their whatever variables that we are interested in, and then assess these averages as if they were the generalizable parts of the phenomenon that we are studying. But it's of course very difficult if it turns out that these averages do not describe any single individual, for example. And in that sense, what I argue in the work is that we should first analyze the individuals, and then we can end up with an idea of so in the optimal case, what we might end up with is a model per every individual, and then we can aggregate those models or the individual level data in the sense that we are not putting this averaging very different individuals and saying that the average person has one testicle or something like this. But what we can do is collate the individual level data and then look at what are the generalizable components across these individual models, for example. So that's one strategy that allows for this generalizability without getting lost in the sense that we can only make statements by individuals. So and it's also a sort of a like a zoom lens sort of a situation. So there's, for some situations, we really want to include lots of details, but often we don't need, we often want to include just the most important details for the context that we are actually interested in and for the thing that we are doing. And sadly, there is no single one-size-fits-all solution for what the main zoom level should be, and this is case-by-case thing then.
It does feel like there's a little bit of a catch-22 here, in the sense of, if we don't know anything, I mean, in order to be able to first data on an individual, to be able to describe their data, it does feel like we need to have some kind of hypothesis that implies a general knowledge about humans in order to be able to collect the data, to be able to model that individual before we then get to the general state. So that seems a bit of a challenge, if you see what I'm suggesting. That at some level, you need some degree of understanding about hypotheses that are fairly general, so that you can decide what needs to be measured.
Yes, and we very seldom start a research project by understanding absolutely nothing about the thing that we are about to start researching. So I think we have this sort of knowledge, and what we often want to do in the beginning is not maybe go to this or directly to this inductive or deductive reasoning mode, but go through the sort of the abductive or the reasoning towards best explanation idea, to try and sort of probe the space. So when there is a lot of uncertainty, what we need to do is try out different things, and then what we'll find is that, okay, so well, this avenue looks promising, and then that's sort of we do more of things that work, we do less of things that don't work, and in this sense we might find that, okay, so well, actually it looks like every time I do this in this context, that happens. And then we might go into the sort of explorations of, okay, so what's the temporal stability of this idea that, or this phenomenon that we think that we have uncovered? Does it hold up in the how much variability there is between people, between different clusters of people, different groups, and so forth. And then in this sense, I think it moves as the uncertainty in this situation gets sort of resolved. We can move into the sort of more hypothesis-based research, and but sometimes what happens is that the environment changes. There's a global pandemic, and the thing that we thought works like that does not work anymore like that. So we need to sort of go back to the drawing board, and we are working this cycle where we reduce uncertainty, then we open up to uncertainty, then we try to reduce it, and so forth.
Mm-hmm. Okay, thank you. It's in this paper, and this comes up several different places, where you're talking about the interesting nonlinear change phenomena that, to me, as I was reading it, did make me think that if you were to build kind of a meta model of behavioral change, that this would be a crucial ingredient, and that does seem to come up in your discussion of the significance of different things you posited, and that is the fact that the individual kind of fluctuation may what's sometimes called critical fluctuation and someone's behavior may predict, anticipate a phase shift, and that is a really quite interesting sort of phenomena. I wondered if there were, could you say a little bit more about that? It seems like that there are a couple of different kinds of studies or results that have suggested that.
Yes, so what you're talking about is often called in these fields the early warning signals, yes, of exactly, sudden shifts. And so there was a lot of excitement about this 5 years ago, and then it went through a drought, and then people are realizing that it's not as simple as we originally thought, but it might be still workable, for example, with this models that are a bit different than what's used in ecology, for example. But the promise is basically that we could monitor a system, and then we could get this alarm that would sort of go off and say that, hey, actually this system might be in the precipice of change. And so in therapeutic processes, this would mean that you would sort of intervene to make sure that the system is not going to go to a worse state than it was earlier. And you can then, so it's like there's in classic social psychology, we have the Kurt Lewin, the freeze-unfreeze idea, where the system sort of becomes more fluid and has more room to move to better or for worse. And this was one of the studies we did that I referred to in this work, where we had these step counts of people undergoing a weight loss trial. And we saw that when this when the system, so it's like when the attractor starts to become more shallow, at the tipping point, the reach between the attractors starts to sort of move like this, then it's easier for the system to sort of start fluctuating very randomly across these different states before it sort of moves back in and settles into one of the attractors. So what we saw in this data with the step counts was that there is this very erratic fluctuation process that happens, and which predicts the individual moving into a week-long sedentary phase. So in this case, if we would have like this real-time monitoring going on, and if there is a lot of uncertainty, as is often the case in these interventions, so we might not know how this person works or anything like that, but we might be able to get this alert that, hey, okay, something might be going on, and so, for example, a software could then produce a ping or deliver an intervention to this person. Or we might have a decision support system in the society that would alert decision makers to say that, okay, so hey, something might be going on. It's not sure that it's going on, but this might be a good point to pay attention and to perhaps see what this anomaly might be about and intervene before it becomes something very bad, which might be the case.
One concern I have at various points in this kind of perspective is it often feeling like you can explain things once they've happened, you know, and this kind of post hoc of like, oh, that was a phase transition. I mean, obviously, what is good, and you know, if such warning signs are diagnostic, that you can monitor them and then say, oh, something is about to happen. But are kind of two questions. One, I'm curious whether there are other kinds of markers of phase transition, you know, that people are vulnerable to moving into another attractor, which may be a better space, or a dangerous space, relapsing, for instance. So are there other kinds of phenomena like this that are perhaps indicators that there's been a change in the attractor landscape? And I also will discuss this in a little more. When we're talking about these changes in the attractor landscape and so forth, are these meant to be kind of metaphorically tell you something that has happened? So, oh, therefore the attractors have gotten weaker, for instance, or do these also have a quantitative meaning, that if it's well developed enough that you could say this is what seems to be happening, you know, and anticipating, oh, we should be getting to a point where there'll be instability in their current state. It often feels like it's after the fact describing, oh, okay, this is what must have happened now. But to what degree, we can go into more depth when we talk about the attractor landscape article, you know, are these really kind of linked to things that can be quantified, or is it mostly useful kind of metaphorically?
Well, for example, in the work where we talked about that I mentioned the step counts, in that sense, we sort of quantified the attractor shifts by this recursive partitioning machine learning algorithm that tries to evaluate the sort of the non-stationarity. So if you have a level here and a level here, then the algorithm sort of identifies that, hey, these are two different levels, and but this is one-dimensional. So this was just the step counts. And in the multidimensional case where we could have many different variables, what we can do is sort of the analysis that we did with work motivation. But in that case, so for example, there was this one example person that we analyzed more in depth, and so they had these different motivation profiles where different tasks sort of fell into, and but it was not. Yeah, so for example, there was this one distinct profile where this person was writing a book, and so it was a very it wasn't very common, but it was distinguishable in the data, but now it's also like how do we know what is an actually meaningful shift? So we can have a shift that is like very small, but still detected by the algorithms, or we can have we can have a huge shift that might not matter for the person. And so in this case, I think currently where we are at is that, so this is, I think this is a very large theme, like what's the difference that makes a difference? How big is, how long is a piece of string?
I mean,
and
is it, and for the interventionist, how do you know, if processes are nonlinear, that when there's no change with each kind of repeated attempt to influence them, how do they know, either by what they need to measure or by theory or understanding control parameters and something, whether they're just ineffective or whether they just need one little more straw to break the camel's back? That seems a particular.
Yes. This is sort of the challenge, and I think that's something for upcoming work, because currently the process is that when there is a straw that breaks the camel's back, people run to the scene and start getting the unique back-breaking capacities of that last straw. and but there are some promising techniques, like in ecological contexts, what people have been looking at are like an increase in autocorrelation and increase of in variance and stuff like that in the time series that predict these shifts before they happen. There's, in psychology, we have this dynamical complexity measure, was used in the step count article I mentioned, but also like some of these like some of these metrics that have been used for this in the ecological studies, like studying climate phase shifts or collapses of societies, they are very slow, and often these increasing autocorrelations or increasing variance, it works nicely for that kind of a system. But often human psychology is not that kind of a system, and what's currently being explored just during the last couple of years is like, okay, so how can we, for example, use this recurrence-based methodology to understand this like these multivariate subsystems and how their connectivity changes, and how that might act as one indicator that's a bit more nuanced or a bit more, takes a lot more information in than the simple ones used in these sort of a bit more nicely behaving processes that have been studied in ecology.
So an interventionist would then have someone actually, focused on the intervention with this particular individual, would have some means of knowing that this isn't just a failed intervention, but rather something in the background in terms of connectivity, in terms of correlation, is changing, so that it's it's not just that they're in a failed intervention.
Yes, and what can of course sometimes be done is that if we have many of such interventions and we have this nice temporal data, then we might actually think about, okay, so maybe we can combine these understandings such that, okay, so it looks like in these kinds of situations, like pushing on just doesn't work. It has never worked before, so maybe we need to think of something else. Or that, well, actually, if you just go a little bit further, it actually you can cross this threshold, and maybe we can find out like what were the control parameters or other factors that were present, and then start understanding. Okay, so what? How would we understand this in real time? But at this moment, I think we are mostly stuck in the understanding things post hoc. And I would argue that also that there will be situations, and I think they will be very common, where causality is only observable before, like after the fact, and we need to sort of acknowledge that we have this certain thing that we are doing, and we need a way to avoid the sunk cost bias, and we need to move on. And sometimes it helps if we do many small things rather than one huge thing. And so these sort of mistakes will be contained instead of spread throughout the whole system. And the evolutionary process can perhaps act upon the whole intervention system if we have many of these sort of intervention agents that are selected upon throughout the intervention process.
Yeah, I saw that you had made that point at some point, and I thought that was really a good one. That, you know, the approach, if you have this understanding of the system as having the strong interconnectivity, then the sort of notion should be that you have this, you have more to gain from really thinking about, you know, the multitude of small things. It does, those kinds, many of those kinds of ideas do seem to assume really having a good knowledge of the system. You need to know what is interconnected, whether in fact they're connected, or whether these different components are really unrelated to some of the other ones in some way. So that, you know, it feels in many ways like the getting to the point of being able to think about complex systems approaches couldn't happen without a long period of a focus and a more traditional linear kind of perspective of kind of building some knowledge of kind of key components. But in the 2021 paper, you know, particularly if you think of someone who's not used to thinking in terms of complexity science, if I'm looking at figure 4, so this is showing the weighted multidimensional recurrence network for the motivation data. And I think someone would say, okay, this is, you know, supposed to help me in terms of visualizing something or understanding the system in sort of way. I think someone would say, well, this is a cool figure. What do I do with this? What does this tell me? Or what do you know where I am in the document? So this is.
Yeah. So what strikes me from that figure is that we see this area that in the beginning, starting from the first time points, there's a lot of these profiles. So each dot is some particular combination or configuration of these variables. So what happens in the beginning of the study is that this person is experiencing states or these configurations that are not repeated in the rest of the time series. And I think that's quite interesting because then because it also raises questions. Okay, so what's happening? Is this person starting to use the survey instrument because they were pinged like between 5 and 7 times a day? Are they beginning to use it differently, or are they beginning to be more lazy about it, or is there actually something that changes in their work? And then we can go back to, okay, look at each of those each of those colors and see, okay, so where is the change going to? Okay, so how do the beginning part and the end part, how do they differ from each other in this time series? And in this case, we had the privilege that should probably be included in all of these quantitative studies, that we also interviewed the person like before and after, and to try and make sense of, okay, so how do they make sense of this data? And so this is, it's very, so these numbers and these quantities that come out of these survey instruments, I think they are very difficult to interpret without actually listening to the lived experience of the person who is doing the data monitoring. Mm-hmm. And so in that sense, I think that this cannot, at least at this point, it cannot be used in in isolation, just this measurement, but and we learned many things about what not to do in this in these sort of data monitoring cases, and I think that also builds upon, like, okay, so how do we sort of then design studies that can help us understand these sorts of data better. But I think that, like, the qualitative and the lived experience component is very important in trying to make sense of any of the quantitative data too. In this case, it was mostly a demonstration that this can be actually done, and it's not just a theoretical idea.
Yes. And pictorially, there isn't something else to take away from the, say, the shape of the kind of cycle, the circle and spiral.
Yeah. The spiral cycle is just a way to make it understandable, because if you would only have a line, it would become
to be able to unpack it and 3 dimensions so you can see it. I thought so. I just would, I think someone looking at it who knows nothing would be like, oh, what does this shape mean in some sort of way? In the what the 2022 paper, which you refer to as Article 3, the attractor landscape paper, very interesting ideas. Very, as with the previous paper, very well done in terms of applying these concepts. So I can find my various questions here. I'm on page 5, just a number of small questions. This is the page where you are first unpacking above figure 3, behavioral states as a valley, behavioral change as movement between attractors, valleys, behavioral influences molding the landscape, hills and valleys. I guess several different questions here. I think I have a better understanding of this issue now, because you earlier under 1, you're saying about associating quantitative valleys with qualitative states is an active area of research and of model validation. I think that's speaking to what you just told me. Yes, that.
Okay. Exactly. So how different, or how big is big? The question that's really not at this stage clear, and it won't probably be resolved for every situation in a one-size-fits-all manner. And that's also why I ended up doing the figure in this paper, where I tried this or explored these different radius parameters, which essentially define, okay, so what makes one configuration of variables different from another. Because
it's not clear in some domains in which you're using some of these kinds of analyses. you have a better knowledge of what radius to use, right? Or criteria for use.
Yeah.
You don't in this, is that?
Yeah, yes, exactly. And there are also like mathematical considerations, because some radius values in some contexts, they you can derive other mathematical concepts when you use this sort of this radius in this case. But so this is a very newly developed method, and we don't have that. And there are sort of these suggestions or suggestions for what sort of parameter values to use that are from different contexts, and a bit might differ because we have this cumulative recurrence network that is multi-dimensional, and there's also something to be said about the sort of time delay embedding that we don't use here for the state space reconstruction. But so there is lots of unanswered questions still in how do we make the best use of this method in this context of behavior change.
But in general, using a wider radius, you're casting a wider net for what's recurrent.
Yes, yes, exactly. So if I have a huge radius, everything is the same. If I have a very small radius,
make sure that my knowledge of it applies. It fits with how it fits in this particular case. So going back to the number 2 and 3, behavior changes and movement between attractors, or behavior change happening because the landscape is actually changing. Can you say more about conceptually really how to distinguish which one of these is happening, whether there's a shock to the system, to the individual, so that there's more movement, or whether there's actually a change in the attractor landscape that those seem difficult to know, which is occurring.
Yes, and I wish I could say a lot more about this at the moment, but alas, I cannot. But the sort of thing is that we know that these things can happen. So we can have the end tipping process where some event jolts you into the new attractor, or we can have the sort of the shallowing of the attractor, in which case I think what we are also hypothesizing in this paper is that you would have this more lasting behavior change, because, well, by definition, if the attractor is not available anymore, then it's very difficult to return to it. Well, I think you might be able to see this by noticing that, okay, so after a particular time, for example, this attractor is never visited anymore. So that might, even though there is movement in the landscape. So this might sort of give us an idea that, okay, so maybe this is something that's no longer available to the system.
Yeah, because if you am thinking out of, using this logic and very different paradigms, you can try to force the person into that and see if they're capable of doing it. But obviously you don't want to do that in behavior change. You could do something in, human movement to say, oh, is that attractor available? To see, can they do that behavior, and you explore whether that seems possible for them. But here, you don't, unless I don't see an equivalent here of trying to, but at least your point is well taken, that if you can see that they never visit that region, that suggests it's not available to them, that attractor is now changed.
But now that you spoke about movement, it also brought to my mind that, okay, so one way of perhaps making better conclusions about this, okay, so they're not visiting this attractor anymore, is to try and sort of nudge the system in some way, and there must be ethical ways to do that, like to shock people and well, shock, because oftentimes because we're not just entities that find a homeostasis and are just completely flat after that, but like heart rate variability, it tells us that like this variability is actually a sign of health. And often we benefit from these shocks. So there could be sort of a research program here that's trying to understand, okay, so how do we, after we have set up this monitoring system, how do we sort of create these pushes that and then observe whether like return times and other things like that from the data. I think that would be very interesting.
Yes, because in, say, human performance kind of skilled action, one of the key things they're often trying to do is develop kind of flexibility and ability to adaptability, and what I don't have a good sense in thinking about these different theories and also thinking about these perspectives is how well, there's a particular concept we'll come back to later, but that kind of, as you mentioned, that ability to respond and in real time to unexpected changes would clearly be kind of a crucial question. And I don't know, I'm trying to think of in any of the underlying theoretical perspectives where that comes in. I'm trying to think of any of the particular theories that really build in, like, this is what we want to train or manipulate people to be able to respond well to the opportunities and challenges of the environment and be flexible and are there particular theoretical perspectives that are better at kind of capturing that as a goal?
Yeah, I'm not sure. I think there's interesting work in sports science that I'm sort of somewhat peripherally involved with now. It's that where they study, okay, so if we throw people into this physical activity intervention and have them keep at it until, because there's this certain threshold that physical activity feels good after you have done a certain amount of physical activity, but because of how the mitochondria are recycled in like lactate and that kind of stuff. But so I think they are building some interesting theoretical frameworks in there. But then there's also so there was just this year, or was it last fall, when there was the first textbook that I think it's coming out this year. The textbook on anti-fragility as a sort of a mathematical framework on understanding how we respond to these shocks and the concave or convex responses that take place in many living systems when they adapt to the results of these perturbations. So I think that might be one avenue that I would be interested in exploring in the future.
Okay. And one other thing that came up for me as I was reading through some of this is you don't talk about control parameters a lot. I'm used to in other areas that being kind of a core concept that people might feel is necessary. Is that going to be important? Is it what those would be? Is that from different theoretical perspectives? Is it clear what those would be? And
yes,
explain what I mean for the audience.
Yes. I think the challenge of control parameters and the order parameters and those kinds of concepts, the challenge is that they are very foreign the people in this field, and I'm especially happy to see like there's the Radboud University group by Fred Hasselman and Merlijn Olthoff, who are sort of, so Merlijn Olthoff is collecting these different definitions of control parameters and looking at ways on how to make them make sense to people outside the perception action or ecological psychology or those fields, because it's often and we need these sort of also one thing that's why that motivated this whole work was that we need these different disciplines to start talking to each other, or with each other maybe rather, because otherwise because there are these things that are very difficult to understand if you come from a very different perspective. So I met one of my or who became one of my main collaborators, Daniel Proverbio. I met him in a complexity conference where he was a physicist, physics PhD student, looking at abrupt transitions in his dissertation work. And it took us, well, we were both like complexity geeks in a sense, but it took like 2 years to find this common language and calibrate our systems to understand each other, and they start working together like fruitfully. But after that calibration effort is done, now I can sort of there's so much we can do, because we can talk about these things and translate these different concepts and ideas to the language of each other. And I think that has been one of the most fruitful things that I have encountered in my career, to meet these people who can do very different things than you can do.
And that I completely agree with you. It really opens up the world when you find people that, and that there's a big gulf. There's a quite big gulf initially in terms of kind of language. When I was reading at some point about kind of the tipping point here again, and this came up as you were talking as well. There are many kind of particular features of more of an attractor sort of view that it's not clear to me, you know, what theories or what particular processes in the existing theories fit well with some of these notions. For the tipping point, you know, or if we're having kind of core questions about shifting between attractors, are there particular models to particular behavioral change approaches that do seem most compatible with that kind of logic? I mean, obviously, there are approaches that are more dynamic, you know, like stage theories and so forth. But do we need to really invent fundamentally the underlying theories to really fit with this, or do some of these map on well?
Well, I think so this was one of the first things that I started thinking about, is like, okay, so we have these stage theories that say that, okay, so a person first goes through this stage and then that stage and then da 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 da, and even acknowledging that maybe the order of the stages is not sort of a linear progression, but they jump and they go back, and then maybe the original sort of idea of a stage gets already a bit muddled. But the idea that every person could actually have their own stages, and like, so this might be like an ideographic idea where we don't have this universal progression of stages, or even the qualitative nature of those stages can differ between like from one person to another. And we've done some research on like qualitative, longitudinal qualitative interviews, trying to look at, okay, so what are the sort of change processes that people themselves describe? And that, of course, has the issue of self-reports and retrospective distortions and all of that kind of things. But to your question about which theories might be, yes, I don't think there is any single answer to this, and I also think that it would be nice to just start somewhere and work with people who are familiar with the mathematical modeling of these attractor landscapes. So, for example, people from physics, and so we one of the first steps would start trying to explain what our understanding of what our theory says. Sort of this phenomenon that we are studying, and then sort of work out in collaboration this model that would give us an idea of the underlying landscape. And there's also yes, well, there are these quantitative methods to derive those landscape from network models that have come up with by the Radboud Group, by Jingmen Cui and others in the last year or two, but they're still at very crude stage. And I think like the wish to have this out of the box solution is not going to be within our reach. I mean, by this I mean like a statistical package that you can just code and use for whatever phenomena, and so I think that will solve. Yeah, so people currently in this field, they suffer a lot from this idea that, okay, so they have this statistical toolbox that they use, and that doesn't necessarily fit the phenomena, and then they go to a mathematician who says that, well, actually what you need to do is look at the phenomena you're studying and then derive the mathematics and all of that for that particular phenomena. And then you go like, well, I don't know how to do that. And this is where you need the collaboration.
Yes. I had one other question, and this was dealing with the societal data in Figure 5. In terms of could you explain for me the principal component data? I'm used to thinking about, I mean, I think people think in terms of kind of traditional ways of thinking about using principal components. How does explain that analysis and interpretation of that, the principal components figure in that?
Yes, so the basic idea is that when people have been studying, for example, the collapse of civilizations, what they've found is that you have this data that at some point, if you only look at the first principal component, so this is also one of these early warning signals of critical transitions. What they've found out is that as the system grows, the connectivity of the system starts to radically change. How much of the system's behavior is explained by the first principal component starts to radically shift. And then when everything becomes connected in the system, like just before a crash, for example, the first component has risen like radically. And so the basic idea is that once you reach these tipping points or these saddles, the principal component sort of gives you an indication of where you are. And so in this case, what I did, I took I looked at the two principal components, and I looked at, okay, so how do these give the same intuitions as is given by the recurrence-based analysis? And so, yeah, so in the panel A, you have the dotted line. So I took one representative radius, and I used those colors to color the points on and the lines on the principal component panel. And we can see quite interestingly that the movement of those principal components, so when it goes to the yellow phase, that's inferred by the recurrence.
I'm sorry, how do I see movement in that figure? So I see the yellow in that last panel C. I see the yellow over here. That's low on or highly negative on principal components, and in the middle on second principal component, and contrast that to the dark, which is high positive on the principal component. And so, what do you mean movement?
Yes. So each point is one.
Thinking of the dates, is that what you mean by the movement?
Yes, yeah, exactly. Yeah.
Okay, I see.
Yeah, so when you are in the yellow state as inferred by the recurrence analysis, then you are in the sort of the middle left portion of the area that's defined by the principal components, and you're sort of rolling around that area for a while. And I thought it was quite interesting because these two completely different methods sort of gave the same idea that, so when you're in when the system is in the yellow state by the recurrence analysis, then it's in the particular area of the principal component coordinates.
Mm-hmm. Okay, so and hence the yellow being very far from the dark red or dark purple or something that. So the meaning of the principal components are, unlike say factor analysis type traditional use. There's not an attempt to try to label, conceptually what these components are, but rather the notion that you're moving through these.
Yes. Exactly. So they are somewhat indicative of the system's connectivity, but here I'm not making these qualitative interpretations beyond that. They represent or can or contain similar information as the phases of the system as derived by the recurrence analysis.
Okay, so that they're really in different kind of spaces in a sense. In your visualization paper, the 2019 paper, this is where you're using demonstration data on the baseline of the Let's Move It trial. And this is a longitudinal study, right? This is the baseline.
Mm-hmm. Yeah.
Okay, so this is ongoing study.
Well, it was finished a couple of years ago, and I think the outcome paper is maybe coming out soon. But
okay.
Yeah, so it's done, and
okay,
we have
it. So a couple of visualization questions, and then wanted to talk about the Figure 6 model and some other minor questions looking at the time. In Figure 1, where you're showing the stacked bar plot, I agree very much with your points that we should be doing much richer kind of data exploration, much use of visualization more and so forth, and that shouldn't necessarily always be hidden in the supplemental, but at least they should be there in the supplemental materials. but I do have a concern about situations where you, in thinking about both our human eyes and our tendency to look for meaningful patterns, even out of randomness, is if you're, say, looking at figure 1, I mean, one of the concerns I have where there's no inferential statistics is much the concern I have when I have undergraduate students who are getting their first data and they see, a tiny difference in their means or some pattern in the figure that is spit out for them by the statistical package, and overinterpret, that if you're visualizing the data and don't have particular information about inferential statistics, isn't there more of a kind of potential problem for people to be looking for patterns and that are essentially not really stable? Kind of a minor question.
Yes, absolutely. And the question that then becomes also is that the statistics tell us about patterns that are stable in the sort of cross-sectional data,
right. Or whether they reflect anything happening at the individual.
Yeah, exactly, and also like we have this because if we do like a statistical test that gives us a p-value, that's like all well and good in some situations. But if you're doing sort of exploratory data analysis, and you would need to think about, okay, so because I need to correct this p-value for multiple comparisons. So what is the appropriate corrections? How many tests should I correct the value with? And that becomes a very deep and potentially unanswerable question, which is why it might be a very good idea to also start thinking about like effect sizes, not in the traditional medium, large, small that are just arbitrary, but in terms of trying to make meaningful comparisons between the variables. And this is also something I wish I would have had time to do with when looking at, okay, so how, like, because in article 2, what I was doing was looking at the sort of, okay, so how many of these time series are, for example, detected as nonlinear? How many are detected as stationary? But that's not really the question I'm interested in. But what I'm interested in is how nonlinear they are, how non-stationary they are, and how much nonlinearity is going to be a problem, or and so forth.
And what is the state of answering that last question? How much nonlinearity is the problem? I would assume it really varies considerably.
Exactly, and that's sort of not a is not a one size fits all answer, and I hope that we will not repeat our mistakes that we did when we decided that, okay, so an effect size of this magnitude is considered medium in all cases.
Well, I mean, the challenge is we also need heuristics to some degree, but maybe when first learning, perhaps only. Looking at your mixed graphical model of this is specifically of the behavioral change techniques, as well as the outcome measures. This is again at baseline. If we think in terms of visualization, would someone say, okay, this is any clearer, this is any easier to look at than, structure, complex structural equation modeling, or make the case that this figure is helpful for our eyes to be able to understand kind of the patterns, any different than looking at, complicated path analysis or.
Yeah, well, with path analysis in this kind of data, it becomes very difficult because you have all of these like paths that fit equally well in the model. Like you can switch the arrows to go one way or the other, and I think that will give a potentially misleading impression of what's actually what might be happening here. But I do admit that the complicated sort of a mess, and one way of other ways of visualizing it is just the sort of looking at these bivariate relationships and putting them, for example, on a on a list that goes from the largest to the smallest, which I think it was in the supplementary material. But what I wanted to do with this figure was to sort of make this give this idea that sort of frames the phenomenon as a network, because when we see these lists and we see these path models and stuff like that, I've found that it gives me a different sort of a feel of what I'm dealing with, and a different intuition. And what I wanted to do is bring this intuition of networks and sort of deliver that to the behavior change researchers with variables that they might be familiar with. And so I think the main contribution of that figure is to sort of deliver the idea that a network is this sort of a thing, and if you're thinking about your data throughout or the phenomenon you're studying through this lens, it might give you a different perspective on how to make sense of it.
I would think that someone coming from a very conventional perspective might say, well, so these different techniques are all interrelated. Shouldn't I use, something like principal components factor analysis to kind of reduce them and use them as a composite measure if they're all combined in this sort of way? Won't that just make more sense, having seen that these kinds of things are all, loading on, probably they put in terms of sort of loading on a similar factor.
Yeah, and that was also sort of the thing, because there's sort of different measurement scales with these. So and because from a substantive point of view, there are some of these things that should be more influential to your behavior the more you do them, and some of these like frequency dependent.
Right.
And there are and others here are just sort of this maybe magnitude dependent, or well, not frequency dependent. So having a physical activity plan made for you by your coach, so you don't, theoretically you should not benefit if the coach gives you a new plan every day or every hour, for example. When you do the sort of loading on principal components, you find that okay, so these frequency dependent behavior change techniques, they differ from these existence dependent visities, and then you're like, well, okay, well, I knew that, and that's sort of a measurement artifact, and this is some like this data is the way to collect these ideas about like what are the techniques that people already do to manage their self-manage their behaviors. This was at this point, it was quite new, and we didn't really know very much about this phenomenon in the first place. So,
in terms of interpreting what you have here at the baseline, is it concerning that, say, the physical data from the accelerometer is disconnected? The survey data for MVPA, moderate to very vigorous physical activity, that the survey responses are connected to networked with the behavior change techniques, but the the data from the accelerometer is out there unconnected. Is that, or is that an expectation? You do point out some aspects in which some of this is expected at baseline. Are you looking for, is the expectation that at the outcome stages that this will substantially change? And is that explicitly a hypothesis, the kinds of things you'd want model, your intervention research to start doing, is making hypotheses at that sort of level of like, okay, at baseline, here's where we are. The underlying prediction is that what will happen is that these will be connected then to the MVPA accelerometer.
Yeah, that's a nice way of thinking about it. Like, and I think it hasn't been done very much. Like thinking about how the connectivity changes from the baseline to the follow-ups. But there are some issues relating to like boring measurement stuff. Like, okay, so we have this accelerometer that people, like, we know that because we also did interviews, and we know that some people went swimming, for example, and they took the accelerometer off. I know that some people wore it for a couple of days, then took it off, forgot about it, and then put it back on. And we know and that kind of stuff. And then the survey might reflect more these things that the accelerometer does not capture, like going to the gym. The accelerometer does nothing to capture weightlifting, for example. But then again, we have this idea that, okay, so you're filling in a survey instrument that asks you about the physical activity, and you're also filling in a survey instrument that asks about this the behavior change technique usage. So there can be a correlation that actually arises because the instrument is what connects these two things. And that's also part of the reason why if you look at the language in which the paper or the analysis is written, it is very careful about making any sorts of definitive conclusions, and it's also one reason. So because I went with the path of the background of this paper is that, okay, so we needed a paper that describes the baseline results, because those are required sort of in the semi-required in the literature, and they don't fit in the outcome paper. And what comes out of this is the most boring paper ever. So when the outcome paper is published, who cares about the baselines? And so that's why I wanted to sort of venture and have this paper do a little bit more than just report this boring data that only serve or are like a handmaiden to the outcome paper. And so it's more like I tried to bring in the idea of this conceptual shift and trying to understand these things from a little bit new perspective, and make quite only a few conclusions about the substantive processes in undergoing the data.
I think that's a great idea. Use that as an opportunity to really kind of examine and test some and demonstrate some of these principles. So I think that was a brilliant idea. My other questions are going to be moving to the interstitial, the text of your thesis that aren't in the papers. I'm not sure exactly what my question is here, but on page 34, I like the way you took figure 1 representing what it was forget now what the particular model was. It was just a visual abstraction of behaviors, environmental conditions influencing an outcome. And you take that figure 1, and then on page 34, you first show a directed network, and then in figure 3, you're removing the assumptions of directionality and independence, and allowing for this coupling people or environments. I guess if I think about, say, a structural equation modeling or, similar kind of looking sort of models in psychology, this still feels different. Now, I mean, obviously the directionality is different, that, you have to decide, are they bidirectional or, what's causing what and so forth but it also kind of feels different. Is that fair, or is it just the kind of how I'm not really sure how to articulate why, it has a different feeling to me, and I don't know if it's because of the origin in figure 1 and getting there, or whether that conceptually serves a different kind of role than the way we'll see kind of models and structure.
I think this feeling that you have is, I think that's a signal of something, and I'm not sure. I'm not sure I understand what you mean, but I'm thinking that it might be what I intended to do here, to build sort of the scaffold and make the idea that these things might sort of feel different, and maybe it's a signal from the embodied cognition that there is
maybe it's just removal of the directional paths where when you see a causal model, it's trying to the purpose is fairly different than when you're just trying to say these are the things that should be connected or likely to be connected, and it doesn't feel like a strong mechanistic kind of prediction you're trying to test in general. I think I have already asked you in some ways about what behavioral principles or what models and so forth are most amenable to really kind of incorporating a complexity viewpoint. But this idea came up for me at a couple of places in your document. That are similar idea asked perhaps slightly differently. When you're talking, for instance, about how parts create wholes and and the feedback being a critical part of this process, you're citing Herrero, or I forget how to pronounce her name. How should interventions be designed to support this notion of this feedback? Or else to disrupt it. And kind of relatedly, you say on page 33 that you're quoting someone who says you want interventionists, leaders need to create an environment from which good things can emerge. So how should interventions be designed this almost goes back to the flexibility idea we were talking about before, of both kind of building in or trying to prevent this notion of feedback as moving the system along, and thinking about a system that does draw from this kind of allowing good things to happen and picking that up. Is it just you stop and retweak the model at that point, or?
Yeah, I think there again is not a one recommendation, and I think that also this might not be. So now we are talking about the applied space, and whereas I mainly tried to stick with the basic science area, but there are sort of like the only mechanism known by me on how people can create the interventions that are smarter than they are is through evolution. And having this sort of a process that allows this evolution to somehow take place. And how exactly, I think it really depends from case to case. But we know, for example, that we have, for example, in decision-making environments. So as the complexity of our environment grows, we must sort of, we're in this Red Queen's race that we must, in order to stay feasible in that environment, we need to increase our repertoire of responses to the challenges. So by Ashby's law, we need to have at least as many responses to challenges that the environment throws at us. As if the environment has more challenges to throw at us than we can respond to, then we are going to start failing at some point. And what this means is that the individuals are becoming, as our environments, the global world is becoming more interconnected, more complex. Any individual will become increasingly inadequate in dealing with that complexity. So we need these sorts of networks of people, and there's a very easy mathematical analysis to show that, okay, so these networks can, if they work well, these networked communities, and we see this in hospitals, for example, nowadays, that we have a team that takes care of a patient, which consists of, say, an oncologist, a psychologist, and a nurse, and so forth. And those should be working sort of seamlessly together. And in the societal decision-making processes, something that has been proposed are these participatory surveillance networks, where we bring in the whole of population or the whole of workforce to weigh in or on some issues and give the diversity, the requisite diversity we need to respond to these challenges that us as intervention designers might never have thought of. And in this sense, so this would be sort of one of these sort of extended minds, and doing less by yourself and doing more with others who are also affected by the intervention.
I did wonder at points about the concept of distributed cognition. Cognition in the wild is sort of notion that, you know, that's part of a system might be really kind of distributed across individuals, and that didn't come up, but that seems a lot of what you're sort of suggesting here. You know, I sort of raised this question in the last paper, but I may ask it more generally. If you're, I know your focus isn't specifically on this, but if one is trying to really truly take a more complexity science kind of perspective, are you suggesting that really the hypotheses really need to be translated for each of these different kind of theories into different kinds of hypotheses about what the effectiveness of the intervention would be in terms of, say, a shift in the network structure, you know, looking for tipping points, or regardless of whether you use it, and maybe hypotheses about specific recurrence results or tractors or critical fluctuations. Does that suggest an entirely new rewriting of the theories, or do you think that, as you kind of suggest earlier, start at particular places, start with particular well-developed theories, or ones more amenable to thinking about temporality differently? But are you optimistic that this kind of approach can lead to a hypothesis-based approach rather than something post-hoc?
Yes. So, for example, we have these like the recurrence methods, measures that come out of recurrence quantification analysis. So, for example, trapping time, which reflects how much the system gets stuck in particular states. So we might see, for example, changes in that variable. And when we sort of have these discussions with substance area experts about what they expect relating this variable that they might not have thought of, or might have thought of, but in very different terms, and not have a quantitative way of sort of measuring it, like for example, hysteresis.
Yes.
It's like people know it's there, but you don't get hysteresis from a regression analysis. So we need to sort of have this discussion and think about, okay, so what are the translations? And this is also like, okay, so like a question. So I'm talking about this bridge building. But and that's sort of the easy part. Maybe well, it's the easier part is to build the bridge. What's not so easy, but what might be like really necessary is to not just build a bridge, but build an island in between the bridges, and have like build the island and steward the flora and fauna on that island together. So that's like, okay, so coming up with something completely new, instead of just translating concepts from this field into the language of this field, but coming up with something that and it might not be necessary in all cases. It might not be feasible in some cases, but in other cases, if we can have this productive discussion about what we actually think and how and what we mean by these things, and maybe something completely unexpected might sort of flower through those collaborations.
The next step would be creating these islands. In terms of recommendations, not in terms of thinking of the hypotheses, but in terms of the tools people can use with the data they get, would you suggest? I'm just wondering whether you would have a suggest that folks who haven't develop the hypotheses in a complexity system sort of way, really analyze their data traditionally, conventionally, and then also analyze it non-linearly. Is that the logic of what you think is what you'd recommend for people? Obviously, at first, I would recognize you'd be wanting them to do much better kind of visualization. Should they always do, analyze something in a conventional way and then do it non-linearly? Or
the thing about the world is that we have this the state we are now in, and the adjacent state that is where we can go from where we are, and we always need to work with where we are instead of where we want to be. And so in that case, I think the most like the easiest adjacent step for many people, if they have, for example, time series data, is to actually run tests and see how nonlinear is this data, how stationary is this data, and sort of like are these relationships that I'm observing in this data, are they consistent across the whole time series, or do they change? So just checking, and after you have checked, then you can do whatever your conscience allows you to do, but at least you have checked, and then you have to of course go to these questions like how large is large, but I think that will be a great contribution to the literature to start these conversations about, okay, so how non-stationary is very non-stationary, for example, in this particular phenomenon that I'm starting.
One concept that came up later in your document, can you just tell me a little more about complexity profiles? You saw that was might be an appealing starting point. Can you explain that to me?
Yes, so a complexity profile is one quantification of complexity. And sort of one of the things is that many papers, they describe features of complexity like feedback loops, nonlinearity, and so forth, but they don't say what they mean by complexity. And in that sense, something I found a nice way to ground or anchor myself is the complexity profile. And the complexity profile is basically like a two-axis system where the y-axis is the number of things a system can do at a particular scale. And the horizontal axis is the scale or inverse resolution. So if you can think about this by, if you're thinking about that you have a camera on top of a concert, and in that, and you can sort of switch the resolution of that camera. So it's like you're watching YouTube, and you can choose like 140 pixels or high definition. And if you have this very high definition picture, you can see how all the individual people move, and you have super lots of information. And then in very low definition, you can only see the major things that are happening. So, for example, when the concert is ending, in the low resolution, you might see, in the lowest resolution, you only see the highest scale behavior. So people are moving, everyone is moving towards the exit, and you can say, oh, there's this movement happening. And in the highest resolution, you have then very much like a redundant information, so that what each individual is doing might be not important in that case. But the thing, like one definition of complex systems is that information across all of these scales. Right. So, and this sort of solves the problem of why would it be more complex if I put myself in a blender and then I have all of these atoms moving randomly? So it seems, because of the randomness, it seems very complex, because I have lots of information. But intuitively, me speaking here, it seems more complex than me having been in a blender. And the answer is that, well, the blended math in the blender is more complex on a micro scale. Yeah, but it doesn't have complexity on the large scales.
So I assume they might be using something quantifying fractality, given what you're saying in the complexity.
Yes, complexity in this term is quantified by information.
Okay. Okay. So I just have a few final questions. I mean, one question I did have is I noticed that one thing that didn't come up in thinking about the relevant existing research were connectionist neural net computational models, simulation approaches like agent-based modeling that and some of those have actually been applied in behavioral health. I'm just wondering, where would you place this in terms of your paradigm shift towards more complexity science?
Yeah, I didn't touch upon those because they had sort of already been discussed, and those discussions, in my experience, hadn't led to very much fruition. Maybe some in some niches, but it never became a thing to do, for example, like agent-based models or something like this. And I think part of it is that many people in behavior change, they really like to see data, and data that they are familiar with. And so this idea of having an agent-based system that sort of gives you the spectrum of scenarios or different things that might happen in this system, it sort of feels unintuitive in a way to many people in this field. And that's why I wanted to use or introduce these models that you could use empirical data as order to the model. And I think those approaches are definitely very important and highly interesting, but I think they are not in the adjacent possible for many of the people who I see trying to make sense of these things in this space.
Okay, well, I would have a couple more speculative questions, but I'm looking at the time, and I assume that we should be trying to complete the examination at this point. So thank you very much. The examination has completed, and I will now provide a final statement. To be successful in taking steps towards really shifting the fundamental grounding, the paradigm of one's domain of research isn't an easy task. As I'm sure you realize, that mere evangelism, just arguing that the paradigm shouldn't be changed, doesn't work. No one will listen to you. You have to have data. And in order to be able to really demonstrate that that's useful, that the technique is useful and useful on data, it does require a researcher to first have a really deep knowledge of the content domain, current state of a particular field. So in this case, the theories and procedures for conducting research, comprehensive, integrative grasp of the field of behavior change, not just one particular kind of theory, a particular motivational approach like self-determination theory, but really a wide-ranging knowledge. You have Mr. Heino has demonstrated this in his thesis. His thesis also touches on phenomena in several different areas, from occupational health, work motivation, to increasing physical activity with intervention, reducing the concerns with behaviors that affect the spread of COVID. His grasp of this area is really wide, and he's precise and careful in his language about the processes, from the small elements, from carefully defining behavior change or characterizing different aspects of the field. In the research presented here and in the thesis, he demonstrates his research skills in each of the areas. Given his goals to be able to complement linear approaches in this domain, to move in a direction shifting towards using methods of complex sciences, he does also have to be deeply knowledgeable and skilled with the linear analysis approaches to really be able to thoroughly grasp the limitations of those. And he has demonstrated the skills in looking deeply at the data, using visualization techniques, examining how adequately data meet the assumptions of the various techniques we're more commonly using in conventional science. And he's demonstrated those skills more than enough. And so in sum, Mr. Heino has indeed met this first criteria, showing deep knowledge of the conventional approaches to conceptualizing and understanding behavior change phenomena. But second, then one also has to, in trying to bridge that gap, have a deep and comprehensive knowledge of the other side, on the other side of the bridge. And on the second point, the candidate has also demonstrated an impressive ability to articulate difficult concepts from interaction, dominant processes, emergence, hysteresis, non-eridicity, really able to explain how an attractor landscape approach could be used and may be helpful to understand. He demonstrates the ability to really understand these techniques in a deep way. So finally, to really be able to particularly create novel and innovative directions for the field to go, and think and link these concepts to a sophisticated understanding of the underlying processes, really also require some creativity. And we see that also in the thesis, that the thesis demonstrates his ability to see what are some of the key points of potential generativity for this perspective. In each of the 3 papers, which I will not go over in detail, I think that has come through in the examination. We see his creativity demonstrated out of these papers. So you also see his ability to kind of focus in on particular kind of phenomena that will be particularly promising. And these have come up, what nonlinearity means for understanding potential abrupt shifts during interventions, understanding potential, the warning signs of that might be implying phase shifts are about to happen. So with the 3 publications that are in this thesis, he is also moving into an area where few people within his research domain have applied these nonlinear dynamical systems approaches. As he notes, there are some approaches that have ideas that lean in that direction. For instance, kind of temporality, but in the broader field of understanding more basic processes of social psychology, there are also some small pockets of research, but really within this domain, those are really quite limited. On the whole, his thesis really contributes substantially to moving the field forward to using these kinds of approach, demonstrating the effectiveness and the promise of these potential approaches and with real data. And he adequately, is able to describe and explain their contributions. I also see a number of other strengths of different sections of the paper, limitation sections, thorough and accurate. The thesis is notable in adhering to the ethics and standards of good science. He's adhered to transparency and open science goals by making his analyses and more supplemental analyses all publicly available. That's going to be particularly valuable given how novel these techniques are in this particular domain. And finally, in his implications and future direction section, he really provides a clear and well-informed vision of where this field should go and where he may be going. So in closing this examination, I propose to the faculty that the thesis be approved.
Thank you, Professor Marsh, for your statement. If anyone present wishes to make any comments concerning my dissertation, please ask the custos for the floor.
You may use the raise the hand option or then the chat option. It seems that there are no comments or questions. So this public examination is completed. Thank you.